Hello everyone and welcome to lecture today. Today we'll be talking about various applications of the double integral. And we'll see that these applications actually extend directly to the triple integral as well when we get to that. But we're going to focus on several different applications in electrical engineering and in mechanical engineering. So specifically related to physics and electrodynamics. Specifically, we'll talk about what's called how to calculate the total mass of a region given a mass density function. And related to that, but in a completely different area, is the total charge, total electric charge of a region. Given some mass or a charge density function. And for both of these two applications, the formulas that we're going to get are going to be very, very similar to one another, almost the same thing. It just, the interpretation of the density function is going to be different. This is all in 2D, so the region R here is in 2D, because we're dealing with a double integral. So we'll then move on to what's called the center of mass. Of a 2D region R. And just like we have, and also have the concept of total charge with the charge density as well as mass density, we can talk about the center of charge. In some sense, the formulas that we derive are going to go together very closely. So these two are going to be very similar to one another. These two are going to be very similar to one another. And related to the center of mass formula, the center of charge formula, we'll have, we can find a formula for what's called the centroid, or the geometric center of a region R. Basically, this is going to be a simplified formula from that we can obtain directly from our formula for the center of mass and for the center of charge. In the last two applications we'll talk about is what's called the moment of inertia. Of a region R. With a distributed mass density, as well as what's called the moment of the charge distribution. Inside a region R. This is related to what's called the possibly the dipole moment and many other things in electrical engineering. So we'll start by talking about deriving a formula for both the total mass of a region R and then briefly comment about how this formula is going to be very similar to the formula for total charge. The main idea here is that we're going to think of having, in general, some region in two-dimensional space we'll call that region R. In any region like this in two-dimensional space, we very often can call, and we do call in applications, Lamina. And that just means you can think of like a flat plate in 2D. So if we consider all of the points on this lamina, very often we can have what's called a mass density defined, mass density function defined all over that lamina. So the idea is that there may be certain regions, maybe like here and here. You can also even say maybe a third region or however many regions you want to consider where the mass is very heavily concentrated. So there's a lot of mass per unit area. In this case, maybe you're measuring in kilograms per meter squared. But as you move around the plate, maybe there's less and less mass. As you move away from these heavily concentrated regions. Until when you get very far away from any of these heavily concentrated regions, maybe the mass density is very, very small. This is one picture that you can kind of think of when you're thinking of a general mass distribution. You have regions of the plate that are very, very highly concentrated, where there's a lot of mass per unit area, and as you move away from those regions, the mass per unit area gets less and less and less. And this is generally the case that's true for most materials. I'd say the majority of materials that you encounter are not all uniform or don't all have the same mass density over the entire material. So the issue here then is that we have to describe this with a multivariable function. So typically for a mass distribution, we say that the mass density function, or the mass per unit area at a point, is a function of x and y. And this is called the mass density function. Similarly, if you have you're dealing with not the application of mass, but you're dealing with the application of charge, you can have a charge density function. Typically in physics, we use the notation sigma for a two-dimensional charge density function. This stands for charge, or electric charge per unit area. This is at the point xy. In general, a mass density function has to be positive or equal to 0 at any point. So rho of xy has to be greater than or equal to 0. But the charge density function can be positive or negative, because you could have positive or negative amount of charge per unit area. That's an important distinction to make right off the bat between these two examples. So sigma of xy is a function that can be either positive or negative. And basically, this density function essentially is you can compute it in general if you know geometrically. You take a very small region. This rho of xy at any point is the amount of mass over the differential area at any given point. And this is important. We'll come back to this idea when we go through the derivation here. But what we'll see, what we're going to justify in just a second, are the following two formulas. At the total mass, or total amount of mass contained in a region R, or in a lamina, is directly equal to, we'll call this M, capital M, just to kind of, for notation. But this is exactly the total accumulation of the mass density function which we directly know how to compute. It's the double integral over the region R of the mass density function. So this is saying that if you have a region R and you have a mass distribution of which you know, or you can approximate the mass density function, you can calculate the total mass contained in that region just by taking the double integral of that function over the region. And the exact same thing is true if instead of a mass density function you have a charge density function. The total amount of electric charge contained in a region R which we'll call capital Q, is directly equal to the double integral, or the accumulation, of the charge density function over that region R. So we'll see in a second an example of how to apply the total mass formula, and we'll stick with the mass formula, but applying the charge formula is the same exact process. You need a density function and you need a region R, which is a lamina, and you just integrate the density function to determine the total amount of whatever quantity the density function is describing in that region. Before we see the example, though, let's just kind of justify this. We want to always justify our mathematical statements, and we're going to do that using Riemann sums. And the way that we're going to use Riemann sums to do that is, again, we always, when we're using Riemann sums, we have our lamina R. This is our region R. We know that the Riemann sum process is the process of cutting up our region R into a whole bunch of very small pieces that we call pieces of, a partition. And we take the limit of this process as these pieces get smaller and smaller and smaller. So we have finer and finer cuts in the partition. This is how we defined previously exactly what the double integral is for a function of two variables. So we're taking this limiting process all the way down until these pieces get smaller and smaller and smaller. And if we zoom in on one of these pieces and evaluate it, so we kind of look at what we're doing here. So we have, let's say this piece corresponds to the ith cut along J and along the x-axis, and the jth cut along the y-axis. So this piece has area delta Aij, and we have to have a sample point here as well that we're sampling at. That corresponds to xi star yj star. And we have a sample point like that in every single one of these rectangles. So the size here is, the width is delta xi and the height is delta yj. So in the limit, as these rectangles get smaller and smaller and smaller, you'll remember that the approximation, or the Riemann sum approximation for the double integral of the density function is actually going to be the same thing as the sum of an approximation to the sum of the mass, right? The total mass of this object, this lamina R, is going to be approximately equal to the Riemann sum Sn, where Sn is the double sum over all of these rectangles of delta Mij, where delta Mij is approximately equal to the mass of a rectangle Ij, or the Ijth rectangle. So if we add up all of those delta Mij's, we're approximating the total mass of the region R. It's not exact, but it's an approximation. And the idea here is that in the limit, as these pieces of the partition get smaller and smaller and smaller, this summation gets closer and closer and closer to the actual value of the mass. Well, we know that delta Mij for very small values of the rectangle is going to be approximately equal to the density at the sample point multiplied by the area of the ijth rectangle, because the density function at the sample point is approximately equal to the amount of mass contained in the jth rectangle divided by the total area of the jth rectangle. jth rectangle. Now this is only, again, approximation because that the actual density is varying throughout the medium, but for small values of delta x and delta y, we have that this is giving us a very nice approximation for a nice density function. And so what that means is that the total amount of mass of the entire lamina itself is approximately equal to the Riemann sum. We'll call this Sn, which is the sum from, and this is different than this Sn, we'll call this the sum from 1 to n, from j to 1 to n of delta mij, which is approximately the density function at each sample point, so that the density function sampled in each rectangle multiplied by delta aij. Which means that the total mass then is equal to the limit of this Sn prime as n goes to infinity, which is exactly the double integral of the density function over the region and there you have it. So this is a very, very nice justification of why this formula should hold and why it does hold in general. So if you want to calculate the total mass or total charge contained in a region, all you have to do is take the double integral of the density function for that region. So let's look at a very specific example to sort of try and see how we would apply this. So let's try and find the total mass contained in the lamina bounded by y equals 0 and y equals 4 times x minus x squared for a density function that has a minimum value of 2 at the origin and varies quadratically with the distance from the origin. The first thing that you always want to do when you have one of these problems is to make a distinction between the geometric domain and the mass density function. So this first we'll consider the domain in this lamina, so the actual shape of the lamina. So it turns out that this function, and this should be y right here. Y is equal to 4 times x minus x squared. So the function y equals 4 times x minus x squared goes from 0, x equals 0, to x equals 1. It looks like this. a downward opening parabola with a maximum height of 1, and then y equals 0 is just this straight line right here. So this is the geometric lamina, or the region that we're considering finding the total mass of. Not only that, but we have an exact, verbal description of the mass density function. So the function that has a minimum value of 2 at the origin, or when x equals 0 and y equals 0, and varies quadratically with distance from the origin, is the following function. This function right here is when x and y equals 0, or you're at the origin, the mass density is 2, and then the level curves of this function are circles. So as you move away from the origin here, you see very clearly that the mass density of this function is increasing as you move away from the origin to some maximum, and turns out the maximum is right around here. This can be made a little bit more clear by looking at the exact domain in a level curve plot associated with the domain itself. So if we open up, this is a Desmos plot of the domain itself. And if we add in some level curves, this first level curve is 2.001. The next one right here is 2.1, 2.2, 2.3, and so on and so forth. This is 2.8 right here, 2.9, 3.1, 3.2, 3.25. You're seeing very clearly that the mass density is distributing, or getting larger and larger and larger as you move further and further and further out. And it turns out that it actually hits its maximum value at a point that you can solve for directly using the methods from optimization before. So if you use the methods for optimization, you get that the minimum value of this function is right here, which is a blue point at the origin, and the maximum value of this function is right out here at this red point right here. I'm not going to go through that calculation right now because it's a little bit long and it's not really relevant to the discussion today, but it's definitely possible to do using the techniques that we've gone over so far. So the idea is that we want to figure out first what the total mass of this region is for this distributed mass. So what we're seeing here is that the mass density is around 2, or 2, if you're using units of kilogram per meter squared, say, it's about 2 kilograms per meter squared around the origin, and as you move out into the further out into the object, the mass density is getting larger and larger and larger until up here it's a value around 3.25, or a little bit larger than that. The actual value of the maximum you can go through and calculate using the methods from before. So the idea is we want to figure out, using our formula, our double integral formula, how to get the total mass contained in this region. So to do this, we need to set up a double integral. Specifically, it'll be the total mass in the region is equal to the double integral over the region of this density function and this region is a non-rectangular region, so we have to be careful with our bounds for integration. but it's the double integral of the function 2 plus x squared plus y squared dy dx. Now what's interesting to note after the last lecture is that very often an integral might be easier to compute if you're integrating over a rotationally symmetric domain. So you might have to use polar coordinates or a different coordinate system to evaluate this integral. It turns out that it's not the easiest way of doing it for this problem, though a good exercise would be to go through and actually do this problem using what we know about polar coordinates. You'll get an integral that will come up to the same value that I'll calculate right now. But I'm going to go through and just do this integral in Cartesian coordinates. That way you can see that. So the idea is that the bounds of this region are going to be for x from 0 to 1. And for y from 0 to 4 times x minus x squared. So this integral is going to go from 0 to 1 for our x bound, and for our y bound it's going to go from 0 to 4 times x minus x squared. So we can do the first integral, or the inner integral with respect to y. Antiderivative of 2 with respect to y is just going to be 2 times y. The antiderivative of x squared with respect to y is going to be x squared times y. And then the antiderivative of y squared with respect to y is going to be y cubed over 3. And this has to be evaluated at the upper bound and the lower bound. So applying the fundamental theorem of calculus here and then plugging in our upper bound and our lower bound, the lower bound is going to be 0, so we don't have to worry about that. And the upper bound is going to be 2. We plug in, we'll get 2 times 4, or 8, times x minus x squared plus x squared times 4 x minus x squared, and then lastly plus 4 x minus x squared cubed divided by 3. So we have to evaluate this integral with respect to x. It's a single variable integral of a single variable function, but evaluation of this integral will directly lead to us getting the actual mass. The value that we compute is exactly the actual mass contained in this region. So, for instance, if we, if our density function, if its units are being measured in kilograms, say, per meter squared, then the value of this integral, or the mass, will have units of just kilograms. So the main issue with this integral is that it's a little bit long in terms of the algebraic expansion of these terms. So I'm not going to go over the algebra right now of how to simplify this. The main trick here is that you have something cubed, so x minus x squared cubed. So you'll have to expand that cubed term out. All right, you can do that using the FOIL procedure or Pascal's triangle. Right? If you remember from say, a high school algebra course maybe, if you compute what's called Pascal's triangle, this gives you the coefficients of different powers of the expression a plus b. So a plus b to the 1, the coefficients of a and b are just 1 and 1. A plus b squared, the coefficients of a and b are going to be, and I should say the different powers of a and b are going to be 1, 2, and 1. Right? So a plus b squared is a squared plus 2ab plus b squared. So the third row in Pascal's triangle give you what the coefficients of a plus b cubed are going to be. It'll be a cubed plus 3a squared times b plus 3ab squared plus b cubed. And you can use this trick to get the coefficients for any power of a summation of two variables, but that's what you have to do here with this cubic term to figure out exactly what this simplifies to. But once you go through and you do the algebra on this, it turns out that this simplifies to the following. It's going to simplify to negative 64 over 3 times x to the 6 plus 64 x to the 5th minus 68 x to the 4th plus 76 over 3 x cubed minus 8x squared plus 8x. So this function that we're integrating here, once you simplify it as far as possible in terms of expanding it out in terms of x, right? This is exactly what it simplifies to. And the antiderivative of this is very, very straightforward to go through and get, because we can just go term by term, and we know that this is going to be the same thing as the antiderivative of this is going to be negative 64 over 7 times 3, or 21, times x to the 7th, plus 64 over 6 times x to the 6th, minus 68 over 5 times x to the 5th, plus 76 over 12 times x to the 4th, minus 8 over 3 x cubed, and lastly plus 8 over 2 x squared. And this is evaluated at the upper bound of 1 and the lower bound of 0. So plugging into this expression will give us the following calculation, or the following sum. So we plug in 1 here, we'll get negative 64 over 21 times 1 to the 7th plus 64 over 6 times 1 to the 6th minus 68 over 5 times 1 to the 5th plus 76 over 12 times 1 to the 4th minus 8 thirds times 1 cubed, and then plus 8 over 2, which is times 1 squared, which is just 4. And then when you plug in 0 here to each one of those x values, you get 0. So this number simplifies down when we bring everything to common denominator to the fraction 59 over 35. And if you're using units of kilograms per meter squared, say, this means that the total mass contained in the region with the density function given is 59 over 35 kilograms, or approximately 1.6857 kilograms. So there you have it. You have that if you have this region, this specific lamina, with this specific mass density function, integrating that mass density function over the region will give you the total amount of mass that's contained in that region for that distributed mass density function. So this is a very, very nice procedure that we have, and it's directly applicable to the concept of charge density as well. If instead you have a charge distribution or a distributed charge density function, the double integral of that charge density function will give you the total amount of charge contained in the region. And typically the charge density function could be potentially measured as, or in units of, it's a sigma has units of, say, it'll be coulombs per meter squared, say. That's a potential units for our charge density function. So that this is the first two applications that we have for the double integral. The next applications are what are called the center of mass or the center of charge. And just like before for the previous application, these two formulas that we're going to get are going to be directly interchangeable again, so you can use them for a mass density function or a charge density function, and their use is very similar. It's going to involve calculating a couple different double integrals that are directly related to the problem at hand, which is essentially solving for, in some sense, the average of the mass density function. But it's a very special average of the mass density function. It's, in some sense, a weighted average of the mass density function, where it's given more weight. It's an average that's given more weight where there's more of a mass density, and less weight if there's less of a mass density. So we'll review what the center of mass is for finitely many masses in 2D. So the center of mass for finitely many masses in 2D, because it turns out that this formula is going to be very important, and we're going to directly apply this to our concept of Riemann sums. So let's say that I have n capital N masses and with a mass, the kth mass has mass mk. So mk is going to be the mass of the kth mass. So this say could be m1, m2, m3, m4, and so on and so forth. So assume that you have n masses. The exact value for the center of mass of these n masses is going to be the sum. This is a vector, right? So it has two separate coordinates. There's an x coordinate and it has a y coordinate. So it's the sum from k equals 1 to n, the sum over all of the masses of the mass of the kth mass times the position of the kth mass. And this will be divided by the sum of all the masses. This is sometimes, this quantity here, this sum is sometimes called the x moment for these n masses, or not the x moment, well actually let's kind of, before we talk about the x moment and the y moment, we'll kind of plug directly into this formula. Right, this formula is saying that for these masses, the x center of mass for the n masses and the y center of mass for the n masses is going to break down. When we plug in that RK here is the position of the kth mass, the vector position of the kth mass, this formula is going to break down to being the sum from k equals 1 to n of mk times the x location of the kth mass divided by the sum of the n masses. This is xcm, the x location of the center of mass of these masses. And then the next component of the vector is going to be ycm. Or just for short, I'm going to call this sum of the n masses mn. The sum from k equals 1 to n of mk times rk over m. It's the same thing as this right here. And the y center of mass is going to be the same thing. It's the sum from k equals 1 to m, but it's of mk times yk over the sum, or the total amount of mass present. And in general, the center of mass of these masses is going to be a point. I've got a point x, y, and that point, xy, gives you in some sense a weighted average of the sum of all the masses. So it's the center, in some sense it's an average, but it's a weighted average of the center of all of the mass distribution. But this is the general way of computing the mass center of mass for finitely many masses. So what we want to do is extend this formula now to a continuous formula, to a distributed mass density function. And this is going to happen again, just like before, using Riemann sums. So we'll start off with our justification and then circle the final formulas that we get. So recalling our Riemann sum procedure, remember that for a lamina R, our Riemann sum procedure involves cutting up R into a whole bunch of very small pieces. each piece of which has a mass that's approximately equal to the density function. Let's say take this piece right here. Let's say this is the ijth piece. The mass of the ijth piece is approximately equal to the density function at a sample point in that rectangle multiplied by the area of the rectangle. So the center of mass for a given Riemann sum, or a given partition of our interval, well, in general we'll have n squared total pieces. So our number of finite masses will be n squared if we have n cuts along x in our partition. So n pieces along x, and then n cuts along y as well. So that the total number of pieces is going to be n squared, and we can directly approximate the center of mass. The center of mass for a given, using the formula from before, the center of mass for these n pieces is going to be equal to the summation over every piece, which is the double sum from I equals 1 to n and from j equals 1 to n of the mass of that piece, which is delta m ij, times the position of that piece, which is the sample point, and this is going to be divided by the sum of all of the masses of each individual piece. So again, we'll call it, this is our sample point. This point is Rij star. Well, we know that Rij star is just the sample point in the ijth piece of our partition. So it's xi star, that's its x component, and yj star is the y component. And delta mij is the same thing as the density at the sample point multiplied by delta aij. So it's the density at the point xi star yj star times delta mij, because this is delta m, or times delta aij, not delta mij. Delta mij is the mass of the ijth rectangle. So that mass is approximately equal to the density multiplied by delta aij. And this is divided by the sum over all of the pieces of the partition of, again, delta mij is a row of xi star yj star times delta aij, or the density at the sample point in each subrectangle multiplied by the area of that subrectangle. And we have to add everything for each one of these terms. So in the limit, as n goes to infinity, or as this partition gets smaller and smaller and smaller, right, we have two separate integrals here. We have that the numerator in this fraction in the limit as n goes to infinity becomes exactly what's called my, or the double integral over the region R of, well, so actually before we do my, we'll talk about what it becomes in terms of a vector. Becomes, so in the limit, the numerator becomes the double integral over R of the density function at some point xy multiplied by the vector R dA. So it's this double integral. In the denominator, becomes, these are both in the limit as n goes to infinity, or the number of rectangles gets larger and larger and larger. The denominator becomes the double integral of the density function dA. So it's the double integral of the density function, which we know from before is just the total mass contained in the region. So the formula that we get in the limit as the partition gets smaller and smaller and smaller is that the center of mass is exactly equal to the double integral of the density function times R over the total mass. Or if you remember that R is equal to xy, and our center of mass has two components, it has an x component and a y component, you get two separate formulas. The first formula being that the center of mass, the x coordinate for the center of mass, is going to be the double integral over R of the density function times x over m. That's the x center of mass formula. And the y center of mass formula is going to be the double integral over R of the density function times y over the total mass. And this is a rigorous, justification of exactly why the center of mass formulas hold. Now, in terms of computation, it's probably easiest to remember the following expressions: that x center of mass is going to be what's called my, which is the y moment over m, and the y center of mass is going to be what's called the x moment over m, the total mass. So computing the center of mass, it's most useful to remember these two formulas, and then to remember that the total mass of a region is just the double integral of the density function over that region. The y moment of the lamina with respect is the integral in the numerator of the x center of mass, which is the integral over R of the density function times x, and the x moment is the numerator in the y center of mass. So it's the double integral over R, the region R, of the density function times y. So in general, calculating the center of mass of a lamina involves calculating these three integrals and then plugging them into those two equations for x center of mass and y center of mass. by the way, this can also be directly used to find the center of charge. Right, this exact same, this is the center of mass. The center of charge for a region is the exact same formulas, but with a charge density function. So I'll use capital C instead of capital M. So the center of charge is going to be, we'll call it C y over Q, and the y center of charge is going to be Cx over Q. Actually, I guess to make it very similar to before, I'll probably use Q instead of C. Where Q here is the total charge contained in a region, or the double integral of the charge density function, and Qy is analogous to the moment formula from before, but it's for the charge density function. And likewise, Qx is the double integral of the charge density function times y. So this location will give you the center, or the average location for a given charge distribution, the average center of that charge distribution. So let's go through and we'll use the same example that we calculated before for the center of mass, because in general what you have to do when you apply these equations, as you've seen, is you need to get three double integrals. Three separate double integral evaluations are necessary to use these equations. You need to figure out, for center of mass, the total amount of mass, which is one double integral. We already computed that for our first example. Then we have to compute the moments, so my and mx, both of which are double integrals that we need to evaluate. They're new double integrals that need to be evaluated. So we've already computed the first for this example 1, which is the total amount of mass. We now need to compute the moments for this as well. So we have from part 1 that the mass of this region is 59 over 35. So the y moment is the double integral over this region of the density function times x so our bounds remain the same. We only have to figure out the bounds once because the region R is staying the same. And our density function was 2 plus x squared plus y squared. And dA is dy dx. So computing this integral will give us the correct value for the moment, the y moment, which we need for the x center of mass formula. So the integral of this function is the same thing as the integral of 2x plus x cubed plus y squared times x. And so the y integral of this is going to be 2xy plus x cubed times y plus y cubed x over 3. And this is, you have to evaluate this from the upper bound to the lower bound. And so when we plug in for y, we get that the y moment is equal to the integral from 0 to 1 of 2xy will be 8x times x minus x squared plus x cubed times 4x minus x squared plus 4x minus x squared cubed times x over 3. So this is the integral that we have to go through and evaluate. And just like before, it's a little bit long in terms of the algebra. So I'm going to let you go through and do the algebra on this one, where you expand this cube out and then figure out exactly what function in the parentheses this is. But when all is said and done, you simplify that and you do the antiderivative of this expression just like before, the correct value that you should get is going to be 32 or 92 over 105. This is going to have units of kilograms times meters. And because the mass density function has units of kilograms per meter squared, and this dA has units of meters squared, and this x has units of meters. So when you multiply all these things together, you end up getting just kilograms times meters. So that's the correct units for the moment. I went out and I showed you how to get the y moment. The x moment is very, very similar, only you have to take the double integral over r of the mass density function times y, at least the x moment, which will be the double integral from 0 to 1, from 0 to 4x minus x squared of 2 plus x squared plus y squared times y dy dx. And again, this is you're gonna go through to do the integral with respect to y of this function right here. So you have to factor through y, multiply through by y, do the integral, expand it, and when all is said and done, when you do this integral, you end up getting that mx is equal to 32 over 45. There's no specific reason that I'm using kilograms and meters here. Really, this applies to any shape, any size, any units you want to use. But just kilograms and meters are, I guess, standard SI units. So what we've shown is that my is exactly 92 over 105. Mx is exactly 32 over 45, and the total mass from the first part is exactly 59 over 35. So what we have then is we have an exact means of calculating the exact value of the center of mass. The center of mass is going to be x center of mass is going to be my over m. which is going to be this 92 over 105 divided by 59 over 35, which is our mass from before. The units of this are kilogram meters, the units of this are kilograms. So the final answer for the x center of mass is going to be 92 over 177 meters, which is approximately equal to 0.51 meters. And similarly for the y center of mass, you get that that's mx over m, which is 32 over 45 divided by 59 over 35, which is exactly equal to 224 over 531 meters, which is approximately 0.42. And if we go and we kind of look at the plot of this region with the level curves from before, we'll see exactly that we can plot out these 2 points. So if I graph out this point right here, which is exactly 92 over 177, and the point y equals 224 over 531, or as a point, this point right here in the middle of the intersection of these two lines, you see that the center of mass for this region is right here, which is definitely not in the center of the region. It's actually different than what's called the centroid of the region, which is a little bit easier to calculate. We'll show that in just a second. You see that because the mass distribution is more heavily weighted on the outside, or on the right, upper right of this material, the center of mass gets pushed up quite substantially from where you would expect it. It gets pushed out a little bit from the centroid because there's more distribution of mass on the outside of this material than on the inside of the material. So this is just a nice plot verifying our previous calculations and verifying that they're correct. The centroid of a lamina is essentially the geometric center of the region R. And this is different than the center of mass of the region. And in many ways it's actually easier to calculate. The main idea is that we assume or pretend that the center of mass, we use the center of mass formulas and pretend that the density function is constant. So the density function is equal to c. Even if the density is non-constant, so like in our example problem where we have a non-constant density function, we just for momentarily pretend that the center of mass is constant and use our center of mass formulas, in which case the following happens, right? The center of mass formulas are the double integral of c times x, or I should say the double integral of the density times x over the double integral of the density. And if the density is constant, then the c factors out and you get the double integral of just x over the double integral of 1, which is the same thing mathematically. We saw this before in our applications lecture as the average value of the function x over the region R, or the average value of the x coordinate in our region R, which is why we can also think of the centroid as the average center of the region R. So we do the exact same thing for the y centroid, where the y centroid is, we pretend momentarily that the density function is constant in our region, and evaluate then what happens when the density is constant. It reduces to the formula, the center of mass formula reduces to the formula for the average value of the y coordinate in our region R. So notationally speaking, we say that the x bar, or x with a line over it, is the centroid, the x coordinate of the centroid, and y bar, y with a line over it, is the y coordinate of the centroid. And so when we do this calculation, we use these formulas for our region, our example. We get that the geometric centers, or centroid, of our region is given exactly by our double integral over with our bounds that we found before of the function x over the double integral of the function 1. And y bar is the double integral of the function y over the double integral of the function 1. Now these would be good practice to go through and compute and calculate, but when you do this, you end up getting that the numerator is 1/3, that double integral of the numerator is 1/3, and then the denominator is 2/3. So x bar is 1/3 over 2/3, or 1/2. And similarly, when you go through and calculate for y bar, you get that y bar is 4/15 divided by 2/3, or 2/5. We can directly show this by opening up our plot. So let's open up the plot and take a look at this in Desmos. These two locations, these 2 points, are going to be exactly given by 1/2 and 2/5. Which are clearly different than the center of mass. The center of mass is this green dot and the dashed line, and the centroid is this purple dot right here on the dotted line. You see that these 2 points they're close to one another, but they're completely different. So the center of mass is the average location of the distribution of mass, and the centroid is just the geometric center of the object. And you can clearly see here that if you look at this region, the centroid is exactly, exactly that. So it's the average in x, about halfway in x. You have an equal amount of area to both sides of this object, and in y, you have the same exact phenomena, that you have the same amount of material, say, or the same amount of the object to the top of this line right here, and on the bottom of this line that's kind of wider on the bottom, so that you see that the center of mass is actually around, it's definitely less than 0.5, because there's more material on the bottom, and the geometric average is right in the middle. But it's important to note that the center of mass and the centroid are different values in general. So the last thing that we want to talk about, the last example that we said we were going to talk about today, is what's called the moment of inertia. And this is, again, going to be derived and justified using Riemann sums, just like all the other formulas. And again, what we do is we say that we'll consider the case of finitely many masses, in 2D, and then apply that to our lamina, our continuous lamina. So the moment of inertia for finitely many masses in 2D we'll call IL, and we'll say, let's say we have n masses, capital N masses, and we have a line in 2D, we call it a line L. So this is going to be the x-axis, the y-axis, in some straight line L. Assume we have, again, a number of different masses all distributed around this line at varying points. And each one of these masses has a different mass. This is, say, M1, M2, M3, M4, and so on and so forth. So just like before, Mk is the mass of the kth mass. Also, we'll call Rk the distance of the kth mass to the line L. Perpendicular distance. We define INL, or the moment of inertia, with respect to line L of these masses, the sum over all of the masses of the kth mass multiplied by the distance of the kth mass away from L squared. So this is how you define the moment of inertia. And what that describes is the resistance of the entire collection of masses to rotation about the line L. So this is essentially what the moment of inertia is measuring. It gives you, in some sense, an idea of how much resistance there is, or inertial resistance there is to rotating all of the masses at once around the line L. So the idea is the following. We can directly generalize this formula. This formula directly generalizes in the sense that if we consider our Riemann sums from before, so we have now a smooth laminate make it a little bit bigger, so make it like, so laminate looks like this. This is our region R, and we've partitioned this laminate into pieces. We can directly apply our formula for finite masses, because when we partition our region R into multiple different pieces, each piece is a piece of mass delta Mij, which is approximately the mass density of that piece at the sample point in the piece, multiplied by the area of the piece, So our approximation to the continuous moment of inertia, we also have to have a line L. So let's say we have some line L. Maybe it looks like this. So our approximation to the moment of inertia about line L is going to be exactly the Riemann sum over all of our pieces in the partition of delta Mij times the distance of that piece, which we're measuring at the sample point, squared. So we'll call r of xiyj the distance to xiyj from that line L. So that means that IL is approximately equal to the summation over all of the pieces of the partition of the mass density at the sample point multiplied by the distance to the line L squared multiplied by delta Aij. And so as the partition gets finer and finer and finer, or smaller and smaller and smaller, and this is our Riemann sum, Sn, so IL is exactly going to be equal to the double integral over the region R of the density function times the distance to the point xy in the region R squared dA. This is our general formula for IL. So this is a general formula that you can always use to find the moment of inertia, but we have a couple of very specific moment of inertias that we very often care about when we're talking about a region. The moment of inertia about the x-axis is going to be the double integral of the density function times x squared, because the squared distance of any point to the x-axis is just x squared. The moment of inertia about the y-axis is going to be the double integral of the density function multiplied by y squared and the moment of inertia about the z-axis is going to be the double integral of the density function times x squared plus y squared, because the square distance to any point from the z-axis or to the origin is just x squared plus y squared. So the general formula holds, and you can do it about any line you want, but typically these three values are the three values that we're interested in. This is also, IZ is sometimes also denoted IXY by some authors. So it's important to kind of know both IZ and IXY, but the idea here is that evaluating these double integrals will give you the specific moment of inertia about the specific axis that you want to find that moment of inertia of. And what it gives you, each one of them gives you the resistance to rotation of the lamina around that axis. So I'm not going to go through and calculate the integrals for our example, but I will go through and just write down what the integrals are and what the correct final answers are once you get the integrals. The moment of inertia about the x-axis for our example 1 will be the double integral from 0 to 1 in x, from 0 to 4 times x minus x squared in y of the density function, which is 2 plus x squared plus y squared times x squared. This has a value of it'll be 508 over 945. This is going to have units of kilogram meters squared. The moment of inertia for our y-axis in our example is the integral from 0 to 1 of the integral from 0 to 4 times x minus x squared of the density function times y squared, which is exactly equal to 4,376 over 10,395. And the moment of inertia about the z-axis is the same double integral over this region, but it's of the function 2 plus x squared plus y squared times x squared plus y squared, which has a value of 9,964 over 10,395. And if you approximate these values, you get that they approximate to around 0.43 or 0.53 for IX. So it's 0.537566. For IY, it's going to be 0.420972. And for IZ, it's going to be 0.958538. So this says that if you try and rotate this about the y-axis, this shape, you'll get the least resistance to rotation. You'll get slightly more resistance to rotation if you try to rotate this shape around the x-axis, and you'll get the most resistance to rotation if you try to rotate this around the z-axis. But that will conclude the lecture today. Thank you very much for tuning in. I hope you learned something and had a great day.